So the minute physics video was our introduction to magnetism. Notice it discussed electric currents. It talked about electric currents and electric charges in the context of magnetism. And it turns out that's what causes, as the video talked about, magnetism. It is the motions of electric charges. And so I'm going to give you a little bit of, no, we're not going to dig heavy into math yet, but we will very soon. But I just want to, what's that?
Are you recording?
Yes, thank you. I am recording. But I'm going to give you just some historical information about the development of electromagnetic theory and stuff like that. Some demonstrations to help you visualize things. Just so you know, electromagnetism is inevitably, invariably three-dimensional. So we're going to have to put our three-dimensional visualization brain on. It can be pretty complex, so I'm going to give you some right-hand rules where you'll do funny things with your right hands to figure out what direction the current's going, what direction the magnetic force is, and what direction the magnetic field is. And then whenever I give you the test over, it'll be funny because I'll watch you guys and you'll all be doing like this with your fingers and stuff. And yeah. So anyway. So first of all, magnets are not a new thing. They knew about naturally occurring magnets. The ancient Greeks knew. In fact, the first magnets, at least historically written about, were discovered in a place called Magnesia, I think it's called, which, hence magnets. So naturally occurring magnets, just they're rocks rich in some type of iron oxide. This is magnetite. Hematite is also a magnetic mineral. And the reason that they're magnetic is because when a magma cools, when a magma of a very specific composition cools and solidifies into a rock, the Earth's magnetic field will kind of lock in the magnetic orientations of the electrons within the atoms, and then as it solidifies, it kind of locks that magnetism in. They're typically very weak. Like I got some paper clips here, and this magnetic rock will not have enough magnetism to pick up any of these paper clips. But what I have here is a compass needle, right? So the north is that way. So the red end of the needle, if you look at this needle, the red end points north. The blue end points south, and it's very, very precariously perched there. And so, if I bring the magnet close, then you can detect the magnetic field that way, right? And then I can do this, and this is how electric motors kind of work. Whoop, whoop, whoop. Yeah. Okay. So. Again, not strong enough to even pick up a paperclip, but it is strong enough to cause a deflection in the magnetic compass needle here. Right. So, known about magnets for a long, long, long time, thousands of years. Naturally occurring ones. They're not strong enough to do anything useful. They're just kind of curiosity, until people started using them for what?
For motors.
Well, not for, long before they used them for motors, they were using them for something else. What's that? Compasses, yeah. Because compasses are actually very, very useful in navigation. If you haven't thought about it much, you might wonder why, but if you have a map, because I do this all the time, although I use GPS, yes, and I use preloaded maps on my phone when I go backpacking, but I'll spend a week at a time in the wilderness away from any technology except for my phone and my solar charger, obviously, so I can keep my phone charged. But I got a map. I got a map, loaded on my phone. My phone knows the direction. But and he's been gone for so long now. Senor Denson used to teach Spanish here, and he was the soccer coach. No, I think he quit probably when you were a freshman that year. But he's the one that I started backpacking with him and his brother. Our first trip up in the Rockies, we came across a guy that had been stranded, lost for 2 days, and he ran out of food. So he hadn't eaten in a day, and he was freaking out because he didn't know where he was going, and because his GPS went out, right? His phone broke or something like that, and he was freaking out. And so we had to tell him, well, just follow this road, follow this trail, and when you hit that trail, go that way. By the way, downhill, follow the trail, downhill, and eventually you'll come to civilization if you ever get lost. But the reason that happened is because he didn't bring a backup. When I go, because I'm always alone too nowadays, I bring a backup map, a topographic map, right, that has all the lines on it that show topography that if you know how to read, you can kind of say, oh, that's that mountain right there, right? But you can't orient that unless you got a compass. So you take that compass, you figure out which way is north, and then you take your map and you orient it north. And it makes it much easier to read the topography around you. And so I always have one of those as backup just in case my GPS goes out. So it's good to know how to, obviously in today's world you don't really need to do that. But back in the day, navigating over an ocean, it's impossible, literally impossible, unless you can always know what direction you're headed. And so that's where compasses came in handy. That's why after I think it was the ancient Chinese started using compasses, inner ocean travel actually became possible. Yeah, they should have just used GPS. I don't know why they didn't. Yeah, morons. And if you ever watch the show Vikings, you ever heard of the show Vikings?
Oh yeah.
It's a pretty good show for the first few seasons. The last couple seasons kind of went off the rails, but it is pretty good. And it tracks Ragnar Lothbrok's humble beginnings as a farmer to his eventual ascension to being the king of the Vikings. And that's how he made his name. He actually was one of the first Vikings to actually use a compass to figure out how to navigate to England, where he could, raid and pillage and murder to acquire his wealth, because that's what a lot of the Vikings did. It's kind of terrible, but it was a good show for the first few seasons. So very, very important in the historical development of electromagnetism was compasses. This is a compass right here. Notice as I rotate it, that red needle is still pointing at you guys because you guys are north of me, right? Okay. I don't know if you guys know this. It's not that common of knowledge, but if you have, say, a permanent magnet, we call one end of it the North Pole and one end the South Pole, right? You guys learn that? So a magnet typically has a North Pole and a South Pole. This is a magnetizer here. It's used to actually make magnets stronger. So each one of these magnets has got a North Pole and a South Pole. Okay. These are the two North Poles. They repel. They don't want to be close together. These are the two South Poles. They repel. They don't want to be close together. But the North Pole and the South Pole, North Pole and South Pole. Okay. So like charges, but it's not the same. Like charges, North Pole are opposite poles attract, and like poles repel. Okay. So that's kind of similar. Okay. Interestingly, what direction does a compass point? Compass needle? What direction does it point? Points north. But we know that the north end of the magnet points to the North Pole, right?
Yes. But really no South Pole because it's
Look, this end of the magnet, the red end, is pointing towards you guys. That's north. Here's the South Pole. Oh, wait. Yeah, I'm sorry. Yeah. It attracts the south. The South Pole of my permanent magnet attracts the North Pole of the compass needle. And the North Pole... Okay, I think this is too strong, actually. It's just inducing the magnetism in the needle. I hope I didn't ruin it. Oh! But yeah, if the North Pole of a magnet points to the North Pole of the Earth, that tells us that the geographic North Pole of the Earth is actually the South magnetic pole, right? And the South geographic pole is actually the North magnetic pole. So that's kind of interesting.
It's like electricity all over again.
Yeah.
You should have just done it the other way.
In reality, the South geographic pole is not in the same location.
Oh, yeah. Yeah, that's pretty far away, actually. Mm-hmm. And it's moving. The magnetic pole is always moving. And sometimes they reverse. Right? They've gone through many, many magnetic reversals in the history of the Earth. You guys know that, right?
Yeah. I felt it. Yeah.
So are the poles just arbitrarily named?
Yeah.
North and south?
Yeah.
Just like charges positive?
Yeah. Mm-hmm. Although, Ben, you can't really screw up north and south because, yeah, we're not going to get into that. But, okay. Beyond the scope. Okay, so these basic magnetism, north, south. We'll talk about magnetic fields in depth soon. But what I want to do is show you the most important, as far as our modern way of life goes, the discovery that I'm about to tell you about, probably the most important discovery in the history of mankind. So important that Trenton's sleeping through it. Okay. So, literally the most important. When it comes, if you like using electricity, if you like computers, you like phones, you like lights, you like watches that aren't mechanical like mine, if you like anything that uses electricity, this is the discovery that it all stems from. It all stems from. Yes, they knew a little bit about electricity at this time, but they didn't know anything about magnetism, and without magnetism, you don't get electricity. With the exception of solar panels. Solar panels don't necessarily require magnets. However, the physics of solar panels came long after the physics of electromagnetism. It's much more complex, actually. It took Einstein to start figuring that out. Okay, so what I'm going to do, what I have here is a loop of conductor, which I'll just consider to be a wire. But if you see between the positive and negative terminals here, there's a strip of insulating plastic. So they're not connected over here. Okay. So if I run electricity into this guy, it's going to go over the top, and I can make it come out this guy. Or I can have it go over the top and then around the bottom and then out this guy. But it's not going to go between those two. Okay. So what I'm going to do first is, and this was mentioned in the video, but I want you guys to see it, and in the context of literally being maybe the most important discovery of all time when it comes to how we live today and how we don't, have to go out and spend 80% of our time just fighting to get enough food to survive for our families and that kind of thing. So what I'm going to do, I'm going to run current in from this side and out that side. I got a switch so I can turn it off and on. So current out this side in the presence of this magnet. And there's a guy named Hans Christian Ørsted who made this discovery. And this is the starting point for the electromagnetic revolution. And he noticed that when you run electric current through a wire and you just happen to have a magnet close by, and the story is he just was doing electrical experiments and happened to have a magnet or a compass needle close to his experimental setup. And he noticed that when you run electric current through a wire, it generates a magnetic field. So you saw that, right? Now it's not pointing north. It's oscillating about a point that's been deflected this way, right? Notice the electric current is coming towards you guys, straight at Gianni. And yet the compass needle started turning this way, okay? But not very far. It hasn't turned very far, right? It's a little bit. If I let it come to equilibrium, though, it wouldn't be pointing north anymore. Because if I turn off the current, it goes back and oscillating about the North Pole now. Should probably be zooming in on that. Anyway. When you're talking electromagnetic radiation, the oscillations, yes. And we'll get to that later on. But for now, quiet. Now what I'm going to do is let it go all the way around. So it's going to go over the top of the compass needle and then back below it. I should probably zoom in. For those online students like Caesar. Gosh, that's Caesar.
That's the first time he's logged in.
I don't know. Oh, he's saying something. All one of me. Okay. So now I've essentially put current not only over the top, but now back towards me along the bottom, right? And then when I close the switch, that's substantially more deflection, right? It's noticeable. More deflection here. Interesting. Now, I'm going to reverse the direction of the current. So I'm just going to flip the positive and negative terminals here. So now the current is going to come in through the bottom and out through the top towards me. Anyone have a guess as to what's going to happen?
It's going to go the other way.
It goes the other way. Huh. Huh. Interesting. Now, what you want to know is that a compass needle points in the direction of the magnetic field. Okay? Points in the direction of the magnetic field. So when you run electricity through a wire, it generates a magnetic field. Notice that the wire is moving, as the current goes towards you, underneath it, it creates a magnetic field that points this way, right? If it comes back towards me underneath, it creates a magnetic field that also points that way. If the current was coming towards me on the top, it created a magnetic field that was pointing that way. And towards you on the bottom, it creates a magnetic field that points that way. That's weird, right? It's strange. So let's do another little experiment, and I don't know how this is going to work, so we'll try it because I have to look from the top down here. So those at home, you might see some, I don't know how well this is going to work. I'm going to put 3 compass needles. Let me just show it first. So I got this set up. It's essentially a wire that goes through here and then makes a 90-degree turn and comes up. Okay, so I'm going to have current come in here and then out through the top. Okay. Actually, you guys won't even be able to see this. I'll make a separate video of this and put it on tomorrow's module. So, yeah, that's not good. That won't work. Let's try to make sense of what we just looked at, though. If I had current coming towards you, out of the board, and also into the board down here, the same current, right? Looped out this way and then back into the board. That was the first scenario. We saw that the magnetic field, which magnetism starts with the letter B, so the magnetic field gets the symbol capital B, pointed this way. Okay? And then when we did the opposite, and remember when it was just this, when it was just the top one, it wasn't as big. When I let that guy in, then it got bigger. Magnetic field got bigger. We all saw this, right? You understand? I need to zoom out again. Sorry, guys. This is too much. It's too much. Too much to keep track of. And then when I did this, when I had the current coming in, when I reversed the direction, I had it coming out towards you and then back towards me on the top. So I had this situation. The magnetic field, reverse direction. Weird. Weird. Now, if you want to know why, if you understand how electric charges behave in the presence of each other, you can, with a little bit of special relativity, you can understand why these magnetic fields happen like this.
Why do you like that?
But don't look at, I would recommend not trying to really grasp that until we talk about magnetic forces. So we'll talk about magnetic forces maybe a little bit today and a little bit tomorrow. So don't watch that video until after tomorrow. I would recommend. You can if you want, but I would recommend. So the thing is, what if I put a compass needle here? What if I put a compass needle here?
It would point to the left, wouldn't it?
Isn't that what I had over here? When it was in up here, I had it pointing to the left. Yeah, so wouldn't it point to the left down here?
It would be small, right?
What if I just got rid of this guy?
You told me, Mr.
What about here?
There's no input.
What?
I thought.
What's up?
It points clockwise.
And it points this way here.
Okay.
Yeah.
Snap.
And that's what this demonstrates, but because of COVID and all that, I can't really have you all gather around. If you put a bunch of compasses on this platform here and you run electric current up out of this, then the needles all deflect so they go around counterclockwise. If the current goes down in, then the compass needles all deflect so they point clockwise. Okay? So moving current, which again is the motion of positive charges, or the anti-motion of negative charges, creates, in a wire, if it's confined to a wire and you have a continuous charge flowing in one direction, it creates magnetic fields that encircle the wire. Okay? And it's not like they flow around the wire, they just exist, but that's the geometry of their existence. Okay? And then if I reverse the direction of the current, then the direction of the magnetic field then switches. And that's what we would get. Okay. Very important to understand this. Very important. Now, when you have a magnet, an actual magnet, again, we used to do this on I'll put it on the video, and so you guys can watch it on the video. Here I got a bunch of iron filings suspended in a fluid, right? And so if I put a magnet on there, give it a little shake, then the iron filings align with the magnetic field. And so I'm going to do this and show it on the camera, and then y'all can have a look at the video if you want, or just look online and look up magnetic fields due to bar magnets. And you end up with something that looks like, that doesn't look good. I'm sorry, this would go much smoother if you know, this was normal school. That's pretty good. So you can kind of see the magnetic field lines here. This is going to work.
Can't see it.
Well, you're not going to be able to. Okay, so there's the magnetic field lines, hopefully. I'll put it over here. Looks better on my paper.
You could have a single file.
So if you want to take a look.
Put it in the floor in the middle of the hallway.
So if you're talking about, so this is the magnetic field due to a current carrying wire. And remember, this is the direction of I, i.e. the direction of the positive charge flowing through a wire, which is the opposite of the negative charge flowing the other way. Right. If we're talking about a magnet, an actual magnet, then it acts like charges. If this is my north pole and this is my south pole, they go from one to the other. And you can actually map out magnetic fields by just taking a compass and if you take a compass here, put it here, the north points that way. If you take it and put it here, it points that way. If you put it like right here, well, it's going to point away from north, but towards south. And so like halfway between, it's going to point that way. And it points towards the south pole. The north end of any compass will point towards the south pole. And if you do this an infinite number of times, at an infinite number of locations, what you see is that the magnetic field looks just like electric fields. They point away from north, they point towards south, and they go kind of like this. Kind of like how Henry and Veritasium were talking about in the video. Okay. So that's the direction of magnet. And you probably know that already from like the magnetic field of the Earth, if you've seen depictions of that in middle school and stuff like that. That's how magnetic fields look.
The diagram of how to remove a core from an apple.
What?
What you drew.
Huh?
What you drew, is it a diagram of how to remove a core from an
Yes,
apple?
yes.
You push it and then you pull it.
Oh, sometimes, guys.
These letters that say N and X.
Sometimes, guys. Sometimes. Okay. Throwing me off. What was I going to talk about? And so, one thing that you want to know, if you learn quantum mechanics ever, if you learn or just read about it, you'll read about something called spin, quantum mechanical spin, and it kind of has to do with the up and down arrows in your electron configurations and how those create the magnetic fields. Just understand that it's not like an object spinning. The spin of a quantum particle is an analogy. They named it spin because it's analogous to an object rotating, but it's not the same. It's actually really, really weird and complicated. But it's that spin that's associated with the tiny magnet property, that they talked about, that Henry talked about. And so you can kind of think about the electrons spinning and generating magnetic fields, right? Because of their spin orientation. It's not truly like that, but it's an easy way to kind of at least start understanding why a permanent magnet creates magnetic fields when it can experimentally be shown that charge must be moving in order to generate a magnetic field. If I have a wire here, right? Here's a wire. There's no current going through it. Here I'll connect it to the voltage source, but I won't close the switch. So I know no current's flowing through here. Well, then there's no magnetic field. You have to close the switch and have current actually flow to generate a magnetic field. So there's no magnetic field here. Yet in a bar magnet, there's no charge like moving through a wire like we have here, but the charge is moving because the electrons are always moving, they never stop. And if you have just such a material in which all those criteria described in the video are met, then they actually create a magnetic field that adds and adds and adds until you have a permanent magnet. Now they also talked about how you can force an object to become a magnet if it's metallic. And notice this is not a magnet, right? It's not picking up any paper clips, right? If you have a permanent magnet, it's going to pick up paper clips. This guy didn't pick up any paper clips. He's not a magnet. This is what's called a solenoid. You see the red? The red is wire, and it's just wrapped around the solenoid a bunch of times. The last type of circuit that we learn about in this class is called an LC circuit, where L stands for inductor, because inductor starts with the letter L. And an inductor is simply a solenoid with an iron core in it. Okay, it's not a magnet. It's not a magnet. But the thing is, think about the direction of the wire, right? If I was to talk about the wire generating magnetic field and then wrap that wire around and around and around and around, it's going to concentrate that magnetic field right in the center. Just like it did here. When I let it go around the entire loop, I essentially doubled the magnetic field. If I double the loop, if I put another loop, yeah, I've doubled that magnetic field. If I put 10 times the loops, I've increased the magnetic field in the center by 10 times. If I do that a few hundred times, then I get a really strong magnetic field with the same wire, carrying the same current. Okay. So if I take that iron core and put it in there, then I get a really strong magnetic field from the solenoid that will align the warring domains within the piece of iron and create a very powerful magnet. Now, yes, when I run current through this guy, it becomes a magnet, but it's not going to be very strong. It really needs that iron core in order to generate a really good magnetic field. And so so if I close the switch now, it's not attracting anything. It's not picking up any paper clips. But if I put that iron core in, now it becomes a pretty powerful magnet. Right? And then when I turn it off, right? So you know what electromagnets are, right? That's an electromagnet.
So why does it not become a projectile?
A projectile?
Yeah, like the iron core.
It kind of does. Watch. If you start with it out here, and we'll talk about this later on, but not quite yet. And then I close it.
Oh God.
Even if it's this way, though. It's because the lowest energy state is when it's fully inserted. And so nature likes, being at the lowest energy. What?
The entire basis of railguns is turning on and off those electromagnetic very precise intervals so that it exerts the most force against the
Entire purpose of what?
railguns.
Oh, yeah. Yeah, exactly. Yeah.
Turning on and off electromagnetic.
Yeah, watch the video on YouTube about the Navy's high-powered railgun that they essentially have to rebuild after every 5 or 7 shots because it generates so much heat that it just destroys the crap out of itself. But it's very, very powerful. Okay. So the last thing we'll talk about today are magnetic forces. We'll talk about it a little bit. And this is another thing. This kind of took it to a whole different level. So here I'm going to have a hanging wire, and my magnetic field is going to be generated by these neodymium magnets. They're pretty strong. And I'm going to run some current through this wire that's going to hang down in front of it. If I can get it to attach. So I'll put the magnet right there. This go right. Give me a second, Johnny. Jeez. Get in there. Put that right there. So let's hook this one up top. This one up down here. Now this is going to be pretty subtle. You're not going to see it. It's not going to be dramatic. So you got to look closely. Which means I probably got to zoom in. Zoom in for Caesar. You can barely see this at home, I don't think. All right, let's see what I point out. So here's my magnet, right? So the magnetic field from the magnet that's pointing at the wire is either pointing this way or it's pointing the opposite way, right? It's either pointing towards the wire or away from the wire. And I'm going to have the wire go down because that's the positive. Yeah, so the current's going to be coming down through the wire. Again, this is going to be kind of subtle. So it won't move that much. Let me try to get it into a position where it will be noticeable. You know what, let me make the magnet just a little bit bigger. All right. So when I close the switch, watch the wire. Are you watching? I close the switch now. So it's pretty subtle, right? You see it. So notice the current is coming down. The magnetic field is either pointing towards you or away from you. And the resulting force is this way. What do you think happens if I reverse the direction of the current?
Boy, I wonder.
What was that?
Boy, I wonder.
So now the current's coming up.
Ooh.
Now it goes the other way.
Wow.
So let's see what pole this actually is. This is that's the North Pole. It's repelling the north, attracted to the south. So the North Pole is pointing towards you. So the magnetic field is pointing towards you. I'm going to put the current back the normal direction, or the original direction, so it follows the red. So the current comes in through the top, is moving down. The magnetic field is pointing towards you. Towards you. The magnetic force points this way. Right? Okay. So those directions we need to learn how to actually deal with. We need to learn how to handle those directions. Just like we can magnify the effects of an electromagnet just by adding more loops, I can magnify the magnetic force on a coil of wire by just looping the wire around a bunch of times, like I did here with this green wire. And then if I take my magnets and point them there, now the current is going to be moving around, right, in the presence of the magnetic field that's pointing out towards you. But since I have a bunch more loops, I'm going to magnify the effect. So I'm going to have the current come in this side and go out this side. And because I have so many more loops, we should get a significantly larger effect, even though I took some of the magnets off. So when I close the switch now, it goes away. So right now, nothing. I close the switch. Okay. Now, what do you think? Exercise your minds here. It might be hard. Now I'm going to reverse the direction of the current.
I think it's gonna start spinning.
It's gonna fly off. It's just gonna fall. It's right there.
Or maybe it just goes in the other direction.
Oh, dang it.
This is copper wire. Copper is not magnetic. Copper, if I take this wire, it doesn't attract to the magnet. It's not magnetic. But I can get magnetic forces on the wire by running current through it. Like that. Okay.
Is that related to the thing where it's like if you have a copper pipe and you drop a little magnet through, it'll fall slowly?
Yeah. And I got one of those, and we'll talk about that when we do electromagnetic conduction. Yeah.
Is that pure magnetism? aluminum, it'll like do weird things.
Yeah, yeah. And we'll talk about that. But that's electromagnetic induction, which we'll get to a little later. All right. So what I want to talk about here, I might not have time. So right-hand rules. This is how we can tie all these directions together. Okay. Right-hand rule number 1. I'm not going to write it out because I'm running out of time. You have electric current in the wire. Point your thumb in the direction of the current, the direction of I, the positive charge direction. Your fingers curl around your thumb in the direction of the magnetic field.
Interruption. Couple quick announcements.
See, look,
Before the bell rings,
here,
go to
in,
lunch.
magnetic field goes this way.
From Mr. Kelly, a reminder that today
Out,
is the last
magnetic field goes out.
for Who is Who. Make sure to get this done by 3:30 today. To our seniors,
Hold on, this is seniors.
daily checking your birth.schools.net email. The school's been sending you emails concerning senior events such as prom and upcoming events like senior awards, ceremonies.
All right, bye everyone at home.
Make sure that you're checking this email every day. Thank you.
I forgot to zoom back out. Sorry, guys. Right hand rule. Thumb in the direction of the current, fingers coil in the direction, curl in the direction of the magnetic field.